Last couple trends that we'll look at are electronegativity, which is something that, again, you should be obsessed with. Electronegativity explains lots of properties of atoms. It explains properties of bonds that we're going to look at in the next chapter. Electronegativity is the ability to attract and steal electrons from another atom. And so again, like a lot of first-year kids will try to memorize these trends, and then a week after the test, they got no clue what they're talking about. But electronegativity really is kind of a central concept to a lot of chemical reactions and bonds. So when we say that electronegativity decreases going down a group, we want to be able to explain why. You know, why would something like cesium have less of an ability of attracting electrons than somebody like lithium? Even though, again, you know, the group 1 elements don't necessarily need more electrons, but this trend should apply to all groups of the periodic table. So if we, in general, think about fake atoms, so here going down a group, the radius gets bigger, right? So I might have a smaller radius on the top of a group, and then as I go down the group, the atoms get huge. And so we would say something like, well, these small atoms are going to have a strong attraction for their own electrons. So let's put a little electron in here. E, cute. But now let's say there's a neighboring atom. Okay, so here's another atom. Cute. We'll make him like a relatively small atom. And he's got a little electron out in there. Okay, so if you have a pretty strong attractive force within your own atom, you probably have a good chance of not even attracting like your own electrons, but also electrons from another atom. So going down a group, watch what happens. Let's compare this to a larger atom. So here's my big atom, and then here's just kind of a relatively small atom. He's got a little electron out here, he's got a little electron out there. Now we said just to start with, this is naturally a weak attraction. If you want to get fancy, you could refer to this as a Coulombic force. The force of attraction between the positive nucleus and the negative electrons. Well, it's just naturally weak in a large atom for a couple of reasons. Number one, distance. The electron is far from the positive nucleus. And number two, shielding effect. All those inner electrons and orbitals are going to block the attraction between the nucleus and the outermost electrons. So if this big guy is having trouble holding on to his own electron, the chance that he's going to attract neighboring electrons is probably pretty slim. So as you go down a group and the radius increases, you get a smaller attraction between the nucleus and the electrons within the atom, and then also amongst neighboring atoms. But now going across, we said that the radius decreases. There's a greater attraction between the nucleus and the outermost electrons. Greater attraction because there's a greater nuclear charge. As you go across, you're just filling a particular energy level, but not only are you adding an electron, you're also adding a proton. The more protons, the more positive your nucleus, the greater the attraction is between the electrons within that particular atom, but then also neighboring atoms. So I mean, it makes sense. In general, whenever there's a strong attraction within the atom, there's also a good chance that they could attract electrons from another atom. Electronegativity, it's something that we'll talk about quite a bit when we look at bonding and like predicting ionic bonds. Somebody's usually got a really high electronegativity. That's going to be the ion that will gain the electrons. And then there's maybe another atom that has a small electronegativity. Now here's the other little vocab term, this other trend that we should mention. Electron affinity energy. This might be one that you did not look at in a first year course. Electron affinity energy is energy associated with the addition of an electron to a gaseous atom. It kind of reminds me of ionization energy. They're actually opposites. So here is, we'll call this EA energy. Electron affinity energy is when you add an electron to a gaseous atom. So you're forming a negative ion. You're forming an anion. Now you're probably forming an ion that's more stable. If you're forming something that's more stable, energy is released. This is exothermic. Or in other words, if they gave you like a numerical value, these are usually reported as negative values, just meaning that it's exothermic. It's energy that's released. So usually we'll talk about this in reference to, maybe like the nitrogen family, oxygen family, halogens, atoms that want to form negative ions because that makes them more stable. More stable means lower energy level. So energy will be released. Yes, energy is released. So if, again, they maybe gave me a numerical value, it would be like a negative delta H value. On the flip side, ionization energy was the opposite. So this is ionization energy. That's where you have some gaseous atom and we want to remove an electron. So now to remove an electron, we have to add energy. Now that electron, even though there are some atoms that would like to lose an electron to become more stable, that electron is still attracted to the positive nucleus. So we still have to add an amount of energy to remove that electron. So then we'd form the positive ion and we'd release an electron. This is endothermic. And again, if we look at numerical values, it's always a positive. So these two guys are opposites. We usually reference ionization energy in terms of atoms that would like to form positive ions, that it's more stable to lose electrons. And we usually reference this electron affinity energy when we're referring to atoms that become more stable when they gain electrons. And again, if they're more stable, they should be at a lower energy level, meaning they release energy. So it says that it tends to get more negative going across a period, meaning that we release more energy. As I go across to fluorine in group 2, fluorine would really like to gain an electron. He's got the highest electronegativity on the entire periodic table. Well, he's going to release a lot of electron affinity energy. I should maybe mention that too on this last slide, if you go backwards a minute. The two extremes, if you ever have to plot trends in electronegativity, or maybe they give you 4 elements and they say rank these in order of increasing electronegativity or something like that. Think about the extremes. So here's a beautiful periodic table. The extremes that we're going to reference, fluorine and francium. Fluorine is the most electronegative element. On the entire periodic table. Now, I get it. He's technically not the smallest radius. The smallest radius is helium, so sometimes people will pick helium because they want to think about the extreme corners of the periodic table. But helium really has no business attracting more electrons. He doesn't really need to gain electrons. He's got full orbitals. So the next smallest element, the next smallest radius, is fluorine. He's a pretty small atom with lots of attractive forces, and he only needs one more electron to fill his outermost energy level. Fluorine is the most electronegative on the entire periodic table. Francium is the least. We should plot those. We'll mark those in. Because that, again, would be a typical multiple choice question where they might give you a couple elements across the periodic table and say rank these in order of increasing electronegativity or something like that. Well, francium is a large atom. He doesn't have a lot of attractive forces within the atom, so he's not going to steal other electrons. But he also really doesn't need to gain electrons. He'd like to lose electrons. Okay, so that's good. We should mention that. So going back to this electron affinity energy, often it follows suit with electronegativity. You know, if you are a highly electronegative atom, you really want to gain electrons. And then those are usually the atoms that will have these higher electron affinity values. And for the most part, that does follow across the periodic table. In general, going down a group, this electron affinity decreases because electronegativity generally decreases. As you have larger atoms with less attraction, there's less of a chance that they will attract those other electrons. And again, if I look at fluorine versus iodine, it does make sense. You know, fluorine is highly electronegative, and so he really does want to gain an electron, meaning that he's going to release energy when that happens because he's going to be a lot more stable. Iodine's just a bigger atom, so yeah, he still wants to gain an electron, but he's not going to release as much energy when that happens because he's going to have to work a little bit harder to gain that electron. He's a big atom. Do you notice this slight discrepancy between fluorine and chlorine? I have not seen this on the AP test in quite a while because it is so small. In general, this trend does follow suit. Going down a group, when electronegativity decreases, so does the amount of energy released when we gain an electron. There's a little discrepancy between fluorine and chlorine, and it's really just because of this. They both really want to gain an electron. In fluorine, you're adding that electron to a smaller orbital. Now here it mentions that it's going into a smaller orbital, the 2s versus the 3s. Make note, these are p's. When we're filling the orbitals of the halogens, we're filling the p orbitals. I noticed that earlier. That should be the p's. Okay, so if fluorine's putting that electron in a little bit smaller orbital, there's a little bit more repulsion, and so you just don't get as much energy released. This is important. Fluorine still has the highest electronegativity. He's still the top dog when it comes to stealing and attracting electrons. He's a small atom with lots of attractive forces. He's just not going to release as much energy when that happens. And again, I haven't seen that on the AP test in years and years and years, but it is a trend that I would be aware of. Going across a period, this usually follows suit just fine. As you go across a period, you're going from ions that are typically positive to ions that are typically negative. And so again, as I get over toward those negative ions, those atoms that become more stable by gaining electrons, when they gain electrons and become more stable, energy is released. So they release more of this electron affinity energy. So again, like when you think of like the word affinity, affinity means like you really like something. I have an affinity for chocolate. I'm like a chocoholic. I love chocolate. I have to have chocolate every day. It's the same kind of thing with electron affinity. There are certain atoms that really have a liking for electrons. They really want electrons. So again, that's why it increases as you go across the periodic table. And when we say electron affinity energy increases, it becomes more exothermic. We release more energy. These are the atoms that really want to gain electrons, and they'll become more stable by gaining electrons.